All right, we're going to continue on with the homework, lesson 14A and B, question number 11. Now, remember, there's 4 questions that we have to ask ourselves to see if a radical is in simplest form. Question 1 is, will anything reduce? And on number 11, the answer would be no. Question 2, will a radical break down? The answer is no. Question 3, is there a fraction inside either radical? The answer is no. But question 4, is there a radical in the denominator? And the answer is yes. Now, I need to show you what not to do, okay? So if you're taking notes, don't take any right now. What some people would have the tendency to do is this. They would have the tendency to multiply by square root 7. But what's going to happen if you multiply by square root 7? Well, it has to be distributed. So what's the bottom going to become? 7 square root 7. And then when you do these 2 radicals, you get plus 7. You didn't remove the radical from the denominator. You just shifted it from the right side to the left side. It's still there. It just moved. So multiplying by square root 7 is not going to fix our problem. So we go back in our minds to what makes things disappear, our terms disappear when you're dealing with binomials. And it takes us back in the Algebra 1 book of mine to chapter 7, page 204, and we learn about binomial conjugates. Now, binomial conjugates is where you have the same 2 items, 7 square root 7, but one's a plus and one's a minus. And we know that the result of multiplying binomial conjugates is the what? The result of multiplying binomial conjugates is the difference between the 2 items squared. The difference between 2 squares. Remember that? Here's what the formula looks like. The formula looks like A plus B times A minus B is equal to A squared minus B squared. When you multiply binomial conjugates, the result is the difference between 2 squares. And that becomes a fundamental rule of algebra that we should know from Algebra 1, Algebra 2, etc. Okay? Now what happens there then is the 7 squared becomes a 49. What about the square root of 7 squared? 7. And 49 minus 7 is 42. So by multiplying by the binomial conjugate, we rationalized the denominator. We got the radical off of it. Got rid of the square root. Okay? Understand that? Now, whatever you do to the denominator to rationalize it, you must also do to the numerator to keep your fraction equivalent to what it was to begin with. Now, the numerator is the product of 2 binomials, 3 plus square root 5 times 7 minus square root 7. Let's just look at that numerator situation. Now, how do you multiply 2 binomials? Well, everybody but me just about in the world now teaches the FOIL method on 2 binomials. I don't teach that in my Algebra 1 class, but I'm going to use FOIL method because that's what you are used to now. You would take what people call the first 3 times 7 is 21, and then the outers, 3 times negative square root 7 would be negative 3 square root 7. And then what people call the inners, which would be plus 7 square root 5. And then the lasts, which would be minus square root 35. Everybody said we got that first, outer, inner, last. Y'all know that I don't teach it that way. I teach it according to page 200 in the Algebra 1 book. I distribute the first binomial through the second binomial. Okay? So my new numerator is going to become that. There's no like terms. So my numerator is 21 minus 3 square root 7 plus 7 square root 5 minus square root 35. Nothing will reduce. No radical will break down. There's not a fraction inside the square root, and there's not a radical in the denominator, so that's the answer written in simplest form. So we multiplied by the binomial conjugate and applied the difference between two square rules to the denominator. The numerator, we had to multiply out those binomials, and so we get a pretty messed up new numerator, okay? Okay, any questions on number 11? I'll let everybody catch up. We still have a few more people still writing. The second half of this, the 14b, is dealing with imaginary numbers, and we began to learn about that in my Algebra 1 book on page 24, chapter 2, where we talked about counting numbers and whole numbers and integers, rational, irrational, and then we talked about imaginary, okay? But we said, where does the I come from? What is I equal to? Anybody remember what I is equal to? The square root of -1. There you go. So the square root of -1 is I. So let's remember our imaginary number stuff. First of all, we need to know the definition, I guess, and that is that the square root of -1 is I. You see, there's nothing times itself that'll give you a negative, correct? Because -1 times -1 is +1. When you multiply with the same sign, the answer is positive. So there's no number that when you multiply it by itself, you get a negative. So there was a value created, and that value created is I. Now, I is not a variable. You understand that I is not a variable? It has a real value of square root -1. It has a real value of square root -1. Okay? So let's just talk about a bunch of I stuff. So let's just start with I. I is equal to what? Square root -1. What would I square be equal to? -1. And let's look at why. You would have the square root of -1 squared be equal to -1. So if I is the square root of -1, then I square would be the square root of -1 squared, which is -1. And then I cubed would be this answer, -1 times another I, right? So we would get -I. They see that? And then I to the fourth would be our I to the third answer times another I. Now what's the I times I part? What's I times I? What's I squared? Okay. So the I times I part is -1. So we have the negative of -1 is +1. So I to the fourth is +1. I'm just adding an I every time. I to the fifth. I to the fifth would be my I to the fourth answer of 1 times another I, which would be I. And we're right back to where we started. And so I to the sixth would be the answer to I to the fifth, which is I times another I, and I squared is -1, so we're right back to -1. So what you notice is that I and I to the fifth are the same. I squared and I to the 6th are the same. So what we need to do is memorize I through I to the 4th, and then realize if you add 4 to any of those, or 8, or 12, or 16, you're back to the same thing, okay? So we're going to memorize then that I squared is negative 1. I cubed is negative I to the 4th is I, and I to the 4th is 1, and I to the 5th is I. The value of I is square root of negative 1, okay? So again, we need to commit to memory I squared. We need to commit to memory that I is the square root of negative 1. I squared is negative 1. I cubed is negative I to the 4th is 1. I to the 5th is I. And then if you add 4 to that, I to the 6th, you still have a negative 1. Or add another 4. Whoops, excuse me. I to the 10th would be back to negative I again, right? And add another 4. I to the 14th is negative 1 again. So we get that idea that we're just going to keep cycling through. Any questions on the first portion? Again, we need to memorize what's in green, okay? Yeah. And if you thought I to the 7th, see, here's what you could think of. I to the 7th is like these two together, right? Because it's really I to the 3rd times I to the 4th. So you could say, well, it's negative I times 1, which is negative I. Or you could say, well, if I add 4 to that, I have negative I. You know, I mean, there's different ways you can think it. But anyway, but yeah, if you just add 4 to one you know, or 8, or 12, or 16, or 20, a multiple of 4 added to what you know is right back to what you know. Very good there. Now, what we call this is imaginary. We call this imaginary. What do we call this? What kind of a number? I, 2i, 6i, negative 4i is called imaginary numbers. What do you call it when you have like 3 plus 3i? Complex number. So that's called a complex number. So what we're going to do now is learn how to add, subtract, multiply, and divide, and do exponents on complex numbers, okay? All right, now, when we add, we could just drop the parenthesis, correct? And then do what? Combine like terms. 6 plus 7 is 13. 3i minus 5i is negative 2i. So when it was addition there, we could just drop our parenthesis and combine like terms. Any questions on number 16? Number 17, when there's a minus in front of that parenthesis, can we just drop the parenthesis? We cannot. See, we got to be careful right here. There's an understood 1 that's being multiplied, and we need to distribute it, right? Now, we can drop it on the first one. We're going to have 6 plus 3i. And then we distribute, we're going to have negative 1 times 7 is negative or minus 7. And then negative 1 times negative 5i is positive 5i. So we had to distribute that understood negative 1 through the parenthesis, and then we can combine like terms. So 6 minus 7 is negative 1. 3i plus 5i is 8i, and so we get negative 1 plus 8i. Remember that the general form of a complex number is a plus bi. So we put the I stuff second. Remember that? A plus bi is the general form of a complex number. Okay? Any questions so far? Number 18, we have a binomial times a binomial. And if you use the FOIL method, which again I'm going to do because at this point that's what you are most familiar with. It's been a long time since you've had me multiplying binomials. We're going to take the first here times the first there, 42. The first here times the second there, which is actually your outers, negative 30i. And then we're going to take the second one here times the first one, which is really your inners. 3i times 7 is 21i. And then the second one times the second one is minus 15i. Square. You multiply the numbers, negative 15, and you multiply the names, and you get a new name. And when you multiply with like bases, you add the exponents. I to the first times I to the first is I to the second. Now, what's I to the second? Negative 1. And what is negative 15 times negative 1? Positive 15. And then here we can combine like terms. Negative 30i plus 21i is negative 11i. That's wrong. Negative 9i. And then we still have the 42. And now we can combine these like terms, and we get 57 minus 9i. Any questions on multiplying complex binomials? Okay. So we multiplied complex binomials. Number 18. Is everybody good? I'll let you catch up. Let me give you a second. Now, I want to talk about something again. Oh, I should have made one of those problems like that. We don't leave an I in the denominator, just like we don't leave a radical in the denominator, correct? Just like we don't leave a negative in the denominator. Because when we're thinking about a denominator like thirds, we're thinking about I could take a piece of pie and I could cut that into 3 pieces, and the name of each piece would be a third. Now, we can let the numerator be messed up, but we never let the denominator be messed up. We want it into chunks that we could actually subdivide into, which is why we don't allow a radical or an imaginary number or a negative number in the denominator. We would do things to fix that, okay? And I want to show you an example after. Well, let me just show you one. Let's just say that let's say that this was 6 plus 3i over 7 minus 5i. Well, I don't like that I down there, just like I didn't like a radical down there. Well, how could I fix that? This is not one of the problems on the page. We're just talking about it. Well, how did we fix the radical problem when it looked like that? We multiplied by the binomial conjugate. So if we multiply by the complex binomial conjugate, no, we don't change. We only change the minus to a plus. Okay? So what we would have is the difference between the two items squared. So that would give us a 49, and then what would this be? Well, what's 5i quantity squared? It's 25 times negative 1, right? Because the I squared part's negative 1? Do I need to write that out? I'll write it out just in case. So inside the parenthesis, we would have 5i times 5i, which is 25I squared, but I squared is negative 1. So we have 25 times negative 1 is negative 25. And we have minus a negative 25, which is a plus 25. So the denominator would become a 74. So we would have made the denominator be a real number, okay? And then we would finagle the numerator. It'd be a crazy binomial thing. I just wanted to show you that the concept of multiplying by the conjugate still works, even with the imaginary number, because it's going to create a situation. That's something we may not use that often. I just wanted to show you that the application is still there. Okay, we're not going to finish that. I just wanted you to see that. All right, number 19, the square means what? Times itself. Question, can you distribute that? Why not? Because that's an exponent happening to addition, and we can only distribute onto a one lesser operation. You cannot distribute an exponent onto addition because it's two levels down. You can only distribute one level down on the order of operations horseshoe. Okay? I think it says that on page 171 of my algebra book. Anyway, so we're not going to try to do that distributive. It doesn't work. So what we have to do is what it says, and what it says is to take this and multiply it by itself, which we would do the FOIL method if that's what you're used to. We're going to distribute the 3 through. 3 times 3 is 9. Distribute the 3 through, 21I. And then we're going to send the 7I through. 7I times 3 is 21I. And then 7I times 7I is 49I squared. Remember, when you multiply with like bases, you add the exponents. I'm going to clean up my 49I squared. Okay, so now we realize that this I squared is a negative 1. And then we've got the 49, so we have 49 times negative 1, which is negative 49. So that little piece turns into negative 49. We're going to combine like terms here. 21I plus 21I is 42I. And we still have the 9. And then we're going to combine those like terms. And we're going to have a negative 40, which we would put first, plus 42I to put it in the form of A plus BI. Any questions on 19? We squared a complex number. Squared a complex number. Okay? All right. Good stuff. Appreciate your attention.